Move to the next converter. There's one slide about what is called a synchronous rectifier. This is nothing but a different kind of step down or buck converter as well. So in the buck converter, we don't have a MOSFET here. We typically have a diode, right? We typically have the switch, the MOSFET, and then we have a diode, correct? That's the buck converter we studied last time. We don't typically have this switch, correct? Yes? No? That's what we studied in the last class. What's the advantage of adding this versus just a diode, right? So this is typically used in applications where we are trying to improve efficiency. Why is that the case? So these diodes have a forward voltage, right? V forward of the diode is a certain number. 1 volt, for example, for power devices. The 0.7 you were studying before in 325? So for power diodes, it's a little bit more than 0.7. Typically 1.2, 1.3 volts is the V forward of the diode, right? So if you have any current flowing through the device, you'll multiply the average current multiplied by the forward voltage, and that will give you the average power loss through that diode, correct? How about MOSFETs? How do you calculate the power loss in the MOSFET? But I squared times what? Not here, MOSFETs are not like diodes. The diodes have a forward voltage. Forward voltage times average current. How about the MOSFET? It's exactly, you were talking about, remember we were operating these MOSFETs or BJTs in this region here. Remember the triode region of the MOSFET? We are operating along this straight line characteristic. This is the ID and then VD. And this slope here it's equivalent to 1 over the MOSFET resistance, 1 over R. Remember that from 325? So this resistance is typically very small. This resistance R, because this slope is very high. So 1 over this slope is the resistance, and then it's a very small number. If this slope is very high, then this number is a very small number. So if you look at MOSFET parameters, you will see that these are, if you buy a low voltage MOSFET, this is in milliohms. 5 milliohms, 3 milliohms, 4 milliohms, right? So if you calculate I squared, let's say 1 amp, 1 amp flowing to the diode, 1 amp flowing the MOSFET. So 1 amp times 1 volt is 1 watt. That's in the diode, right? How about 1 amp times 1 amp squared is 1, right? Times 8 milliohms, 8 milliwatts, right? 8 milliwatts versus 1 watt, right? So there's an advantage in using this kind of circuit, but you have to time the device properly. You have to time it such that this device, as soon as it sees that there's current going to flow, remember how does this buck converter work? First we turn on the switch and turn this diode off, right? When this is on, when the switch S1 is on, the diode is off. And then vice versa. As soon as I turn off S1, this diode should turn on, right? So as soon as this diode turns on, you have a sensing circuit to know that this diode is going to turn on. As soon as this diode is going to turn on and you're going to start to conduct current through this diode, you will turn on the MOSFET. Right? That's why it's called a synchronous rectifier, because it's synchronized with the diode turn on. So you'll have to synchronize it with the diode turn on. So as soon as you see the diode turning on, you will turn on the MOSFET. Okay? Then the current will see two paths. Something with a forward voltage opposing current flow, right? Forward voltage of the diode opposes current. Current wants to flow this way. Then the diode forward voltage is like this, right? Opposing the direction of current flow, right? So you have something that's 1 volt opposing current flow versus you have a very small resistance. Where would the current flow? Through the small resistance versus something that is opposing it from flowing, right? So it's called that's why it's called a synchronous rectifier. In that case, the current will flow through the MOSFET, and you will be producing a power converter that's much more efficient, right? And you can do that with a MOSFET, because remember the MOSFET structure was identical. You can have current flow this way through the MOSFET, or you have current flow the opposite way through the MOSFET. right? MOSFET, remember the structure of the MOSFET, it was what? You had like P material here, and N material here, N material here, and this was your gate, right? N, and this was the gate. It's identical, whether you use this contact as a drain and this is the source, or this is the source and this is the drain, it does not really matter. Right? It does not really matter. It's an identical structure. Yeah. So people use it. Of course, the disadvantage is what? It's complex, right? You have to have a sensing circuit to know when current will start flowing in the diode, and then you have to have a gate drive circuit here to turn on and turn off the MOSFET, right? So it's much more complex than just having a diode in there, but it's much more efficient. So if you have a battery-powered application, and this is interesting, then you compare the power losses in the diode versus the power loss in this circuit additional circuitry that you have to install in the system. So it's a compromise. The other alternative, of course, is to use a different diode completely. There are, silicon carbide diodes now that have a very low forward voltage drop. So there are, or Schottky diodes that have very low forward voltage drops. So there are some other diode technologies, but still synchronous rectification will always beat them. So you can try to improve the diode, or you can use synchronous rectification. Right, so it's another type of buck converter, basically. It's a buck converter. I'm just operating this MOSFET as a diode, basically, right? Okay. Next, converters. So we finished the step-down converter, so we'll talk now about the boost or step-up converter. And we'll go through the same analysis, right? We will look at the voltage across. So basically, we are trying to size the switch, the diode, inductor, and capacitor. So for the switch and the diode, we have to know what the voltage is across the switch and the diode, and the average current flowing through them. Same. And then inductor, we do volt-second balance across the inductor to find the inductor size. Charge balance across the capacitor to find the capacitor size. Right? So we will go through that. And then we will assume, same thing, we will assume that we're operating in steady state, there's no transients, switching period is T, the switch is closed for a period of time, dt, and open for 1 minus dt, 1 minus d times t. Inductor current is always continuous, so we're not operating in discontinuous mode. The capacitor voltage, capacitor is large enough when we try to look at the rest of the waveforms, and then we calculate the capacitor size specifically by considering a certain ripple voltage. And then, of course, we assume initially that the components are ideal.
So when steady state conditions doesn't exist?
At the very beginning, initially your capacitor is not charged. So if you're looking at capacitor current, then it's IC is 1 over C integral of the. So what's the initial condition? It will be 0 initial, versus it will be initial condition for current and the inductor. It will be I minimum or I maximum. These will be in my initial conditions all the time. Versus 0. Initially the inductor has no current, right? So, but we're not studying that. That's more of a transient study. After we get to the point where we can bring the circuit to the same analysis as 420. Then you're bringing in the time domain analysis, then you should be able to study transients, right? At the end of the chapter, we will introduce that, but then I will leave that to 420 to study transient of a circuit, because we bring it to that state, yeah. Anyway, so how does this boost converter work? I have a switch here. If I close the switch, what's going to happen? I will be placing this voltage across my inductor, my source. I'll be taking my source and putting it across the inductor. If I put, which means, and the current will flow through this loop, right? Current will only flow through this loop, right? There's a short circuit across all of this, right? So current will only flow through this loop here, which means I'm taking supply energy and dumping it into my inductor. If I keep the switch on for a long period of time, then what's going to happen? I have a positive voltage across an inductor. What's going to happen to inductor current? It's a positive fixed voltage. Inductor current is equal to the integral of that voltage, right? So the inductor current will be a ramp up. Energy stored in the inductor will be half Li squared, which that I'm going to reach to, right? Whatever I am going to reach to will be that energy that will be stored in the inductor, right? So if I keep this switch on for a longer period of time, which means I maintain the voltage across that inductor for a longer period of time, so current will rise for a longer period of time and rises to a larger value, which means I'm storing more energy in my inductor if I keep the switch on for a longer period of time. So I take source energy, dump it into my inductor. Then what do? As soon as I open the switch, right, inductor has energy, right? Where will it go? I have to find an alternative path for it to go, otherwise the voltage will appear across my open switch. Otherwise, LdI by dt will appear across my open switch. So I put a diode to allow inductor current to flow through that diode and then out through to the capacitor and the resistor, right? So I take, if I dump some of the current into the capacitor, what will happen to the capacitor voltage? It will increase, right? So if I keep adding more energy and dump more energy into the capacitor, capacitor voltage will increase. And depending on the size of my resistance, then I can actually raise this voltage to whatever value I want, ideally speaking. Theoretically speaking, if I put this switch, close it for a long period of time, then what does the inductor look like in steady state? Short circuit, theoretically speaking, right? And if this source can, theoretically speaking, provide, if it's a short circuit, then this source is providing infinite current, right? Which means I can theoretically store infinite energy. So if I can theoretically store infinite energy and dump it onto my capacitor in the second mode of operation of the circuit, then theoretically speaking, I can raise my capacitor voltage to infinity. And this is how the circuit works, theoretically speaking, right? In reality, that doesn't work that way because I have a voltage drop due to my inductor copper wire. I have a voltage drop across my diode. I have a voltage drop through my switch. I have a voltage drop across my ESR, right? So there are limitations to the real practical, but theoretically speaking, the equations that we will come up with will show an infinite value if you keep the switch on for a long period of time. So for a large value of D, theoretically speaking, I can have output voltage equal to infinity, which is great, but it's not real. So this is how the circuit functions, right? So now we'll go to the analysis. Same thing. We'll look at the voltage across the inductor when the switch is open, when the switch is closed. We find delta I, switch is open, switch is closed. We know that we're operating in steady state. So any delta I up in the inductor will come down to the same value of I. So the sum of my delta I's will result in zero current changes. Same analysis. And out of that analysis, we will come up with the voltage transfer ratio. So what if I have some input voltage here, what is the output voltage for a specific duty cycle? That's my voltage transfer ratio, right? And then I will come up with equations to calculate the value of L and C. In the meantime, I will also have to look at what is the voltage rating of my devices, right? So if this switch is open, then this diode is closed. What is the voltage across your device?
Yes, minus VR.
No?
Yes,
V out plus what? No, this is an open switch. Why is it plus? That's it. It's V out. This is short. This is short. This is open. So what is the voltage here? It's V out, right? It's the output voltage. How about if this is short and this is open? What's the voltage across this? V out. Same. It's the same. Exact same. Right. So in a buck converter, the switches are rated to the supply voltage. In a boost converter, the switches are rated to the output voltage rating. It's a source plus the inductor voltage. It's fine. But do you know what the inductor voltage is? So it will be the source plus the inductor voltage will definitely be the output voltage. Right? You can do it that way. It's easy. I mean, it's easy to think of it this way. Right? So in general, let me give you a trick. Okay? So typically, any power converter will be like this. Right? You will have an input. One side will have current coming in or coming out. right? Let's say with the motor, the current will be coming out. And then you will typically have your power converter switches here, one switch here, and one switch here. These switches, one can be a MOSFET, one can be a diode, one can be or both can be MOSFETs, right? So, and here you will typically have a source or a fixed or a stiff voltage. So typically, any power conversion circuit can be represented like this. Can be represented as a stiff voltage on one side, and then a stiff current on one side, right? And then you will have your switches between them. I like to redraw it this way. Since the switches can only be on, one of them can be on at one time, right? Not both can be on. If both are on, you have a voltage short circuit across your stiff voltage source, which is a short circuit across your source. That's not good, yeah. So typically I like to draw it this way. I didn't draw it nicely. Right? This represents, this here represents your two switches, but it's either going to be on, the top one will be on, or the bottom one will be on. Right? And I call this a single pole double throw representation. Single pole meaning I call this the pole and these are the throws. Single pole double throw representation. You will find that in the notes at some point here. So, and this is how you can represent any power converter. And you will see that, you know, the throws here are always rated to the stiff voltage. Right? If in a buck converter the stiff voltage was at the input. In a boost converter, the stiff voltage is the output, right? In the buck converter looked like this, right? I had my source here. I can redraw it. You know, I can redraw it versus the way it was drawn. This was my buck converter. This is my load. On one side, I have a stiff voltage source, which is my supply voltage. On the other side, I have my inductor current, which is my stiff current. The boost converter, I can redraw this same way. So this, I can remove this now and draw my single pole double throw representation. I can draw it this way. I can write here. Right? I can draw it this way. This is my single pole double throw representation. And you can draw the boost converter exactly the same way. You can draw the boost converter same way. This boost converter is here. I have my source. Here is my stiff current, right? Stiff current means continuous current, right? We always assume that inductor current is continuous. Continuous means it doesn't change. It's a stiff value, right? So this is a stiff value of current, and then here's my pole, and here are my two throws, right? The top switch is on, which is the diode, or the bottom switch is on, which is the MOSFET. Either this or that, and this moves between top and bottom, right? And the switch voltage rating is always equal to the voltage across the throws, or the stiff voltage across the stiff voltage. And the switch current rating will depend on, okay, which one is the diode, which one is the average current rating will depend on which one is the diode, which one is the MOSFET. And we did that last time for the buck converter, and we'll do it this time for the boost converter, to calculate the average value of current here. So any questions on this? So now let's go and do the equation. So now the switch is closed, the diode is open. Again, the same process. What is the voltage across the inductor? Source voltage in this case, right? Source voltage is placed across the inductor. So inductor voltage is equal to the source voltage, is equal to L di by dt. This di is the change in current during the switch on time. So I will call this a delta I. And then I'll call that period where that current is changing, I'll call that delta t instead of dt. And then I will solve for, and delta t here is what? The time the switch is closed. So the switch is closed for capital D, or the duty ratio time, the period of the duty ratio. Right? It's capital D times t, that's your switch closed time period. So capital D times T is in delta IL. And then you solve for delta IL here equal to some value, right? So this is switch closed. And then same thing with the switch open. What is the voltage switch open here? The diode is short circuit, right? The switch was here. It's an open circuit and the diode is a short circuit. So what is the voltage across the inductor in this case? On one side it's Vs and one side is V output. The output is on the other side of the inductor. So it's Vs minus V output across the inductor. That is equal to LdI by dt. Same sort of logic, but now the only thing that changes is, okay, this is the switch open. How long is the switch open for? It was closed for D, capital D times T. So it's opened for 1 minus capital D times T, because we said that duty ratio is 100%, or 1, right? So if it's closed for 1 minus, if closed for D, then it's open for 1 minus D, open for a period of 1 minus D. And then same thing we solve for delta I. And then we have my delta I open, delta I closed, and delta I open. The sum of these two will bring the current back to its same steady state condition. So we add the two up, and we say that fine, because we are operating in steady state, the current will not change, so the sum of these two is 0. And then we just take the two equations that we derived before, and then from there we come up with, we solve this equation for the voltage transfer ratio of this boost converter. Right? If we look at this equation, what is the minimum value of the output?
Just be yes. No, minimum would be.
Yes, you're right. So the minimum value would occur with it at the duty ratio of 0. Because remember, we said that duty ratio is the amount of time I keep the switch on. If I don't put the switch on at all, I'm not storing any energy from the supply into the inductor. That energy from the supply to the inductor is what is going to be dumped on top of the capacitor to raise its voltage. So now I don't have that. I keep the switch open all the time. If I keep the switch open all the time, then this is a steady state. Inductor is a short circuit, and capacitor is an open circuit. So what is my output voltage? Vs, the source voltage. So it makes sense, right? So, and then the other extreme is when D is equal to 1. When D is equal to 1, what is the output? Infinite, right? And that's what we said initially, right? Theoretically speaking, if I keep the switch on for a long period of time, then I will take, and I assume that my source has an infinite amount of current capability. If I put a short circuit across a source with infinite current capability, then I will have infinite current flowing through this inductor, and then I can store infinite energy, and I can take this infinite energy, dump it into my capacitor, raise its voltage to infinity, right? That's the theoretical explanation here. So that's the case truly if I don't include losses. We will see the analysis if I include some losses here. But so we will see the drawing of this next. So we found now the voltage transfer ratio. And we know the voltage, the peak voltage across the diode and the switch. Right? They were equal to the capacitor voltage, which is the output voltage. Right? So now what? Now we need to find the inductor and capacitor size. Correct? So we know the voltage switch, and then we need to find inductor size. How do you? And we know the voltage transfer ratio, and then we want to find inductor size. So the way we will find inductor size here is same. You know, we first find the minimum or critical value of inductance to maintain continuous current. We will do that, and then that's the minimum value. And then we will use the equations or the waveforms to be able to calculate the actual value of inductance for a certain delta I. And that's from the delta I equations that we have here. You know, if I bring the inductor here and specific, so I have a specific ripple current and a specific area under the voltage curve. Remember that area under the voltage curve that we said that inductance is equal to the delta lambda, which is the flux linkage, which is the area under the voltage curve, divided by my current ripple. Right? How about capacitance? Exactly, it's the area under the current curve, which is charge, divided by a specific voltage ripple spec. Right? So inductance and capacitance, very easy to calculate here. Okay, so how do we come up with minimum value of current? So let's first go back to the circuit and look at where. So this is my circuit here. What is the average value of inductor current? Average value means steady state. If I'm assuming this circuit is gonna operate in steady state condition, what is the average value of my inductor current? What do you think it should be? Exactly, it's also equal to the average value of my load current. Average value of inductor current, is it? Average value of inductor current? No, it's not equal to the average value of inductor. Average value of inductor current, here, remember it's... so I will have some inductor current. This inductor current is coming through here. And then its average value will be divided between this and this.
Is that when the switch is closed?
So when the average value of... So this, let's assume this has an average value of IL for now. Okay? What is the average value of switch current?
Is it half of IL? It's like half or
Exactly. So what is it? Remember, it will be, what is the current that will flow in this device? How will it look like, approximately? When the device is on, there is current. The device is off, there is no current. Fine, there may be some ramp to it, but forget about that. Assume it's a square wave. Right? If we assume it's a square wave, then what is the average value of the square wave? Exactly, it's the duty cycle times the peak. Right? So the peak would be the inductor current in this case. So the average value of switch current would be D times IL. Average value of diode current, 1 minus D times IL. Right? So we now have the switch peak voltage and we have the switch average current. Right? Now we would like to see what is the inductor current. So the inductor current is obviously going to be a combination between them. Right? So when the switch is closed, I'm applying Vs across the inductor. Right? It's a positive value of voltage across the inductor. So what's going to happen to the inductor current? I is equal to 1 over L integral of VL dt plus initial condition. Right? So assume I start with a minimum value. My initial condition is a minimum value. What will happen to inductor current for when I have switch closed? To ramp up. Right? And how about when the switch is open? And when the switch is open, I have Vs on one side and V output on the other side. Which is bigger? V output is bigger. It's a boost converter. It's a step-up converter, right? So it's Vs minus V output, but Vs minus V output is a negative number, right? So if I have a negative voltage across the inductor, what will happen to the inductor current? It will ramp down, right? Do we agree? We agree? Everybody is fine with this? So this portion of the current will flow in the switch. Right? Because the switch is closed, you're pushing inductor current through to store energy. And then this portion of the current will flow through the diode. Right? So if I ask you to draw switch current, it will only be this red portion with 0. And then another red portion like it, and 0. And if I ask you to draw diode current, it's this green waveform. Right? This has an average value. Okay? That's the average value of inductor current. Okay.
Is this all assuming inductor current is
Continuous. Yeah, we're always assuming inductor current is continuous. Discontinuous, we will not analyze it. We'll just use the equations in the textbook. I will not go through the analysis of discontinuous. We will introduce discontinuous current and we will show that what changes, but we will just use the final equation in that case. Yeah. And the final equation is the same. We will still have a voltage transfer equation, and that's going to give us the ratio between output voltage to input voltage and duty ratio. right? We will, same thing, and then we will still have an inductor to calculate inductor and capacitance. But we will see that, and we can still do that from the waveform. Same, nothing changes about calculating inductance and capacitance. Inductance is always area under the voltage curve divided by delta I. Capacitance is always area under the current curve divided by delta V. It's just that these waveforms will change if my current is discontinuous. The area will be different, right? So what is minimum inductor current? Minimum inductor current is equal to average value of inductor current minus my ripple divided by 2. Maximum inductor current is equal to the average value of inductor current plus ripple divided by 2. What is average value of inductor current equal to? Average value of inductor current is equal to something calculated from here. So how did they calculate average value of inductor current? We looked at input power and output power, right? Input power is my source voltage times average inductor current, right? This is my circuit. My circuit is here. My circuit, what is the power current coming out of this? It's the average inductor current, right? The average value of battery current is equal to the average value of inductor current, right? So the power at the input, or the power transmitted by my power source, is the average value of voltage multiplied by the average inductor current. How about the power at the output? It's the average value of voltage squared divided by my resistance. Right? That's I can equate input voltage, input and output. And then I have a relationship between my average value of voltage now and some other parameters. Right? I have a relationship between average value of voltage and then my source voltage and my duty ratio. So I will use that and I also have a relationship between, with my delta I's and my inductances to utilize for my delta I calculation. So let's see what we do here. So we can equate the input power and the output power, right? Output voltage is from the voltage transfer ratio, right? Vs over 1 minus d. It's Vs over 1 minus d. Vs over 1 minus d squared divided by R. That is the output voltage. I mean, this is a rearrangement of it, right? I just rearranged this, okay? And from here, I can calculate the average value of inductor current, right? Because the average value of inductor current is equal to the average value of battery current, in this case. So I can calculate the average value of inductor current from there, and I use it to substitute in the minimum maximum equations that I want, right? I want minimum and maximum values of current so that I can do what? Equate the minimum to 0. If I equate the minimum to 0, that is the critical value of inductance to maintain continuous current. So I do that, and I solve this equation. So I equate this to 0. I equate this to 0, and I solve for inductance. That will give me the minimum value of inductance in terms of circuit parameters. Okay?
Assuming no losses.
Yeah, there's no losses. Again, typically, always you will design your first iteration will be without losses. And then you will do a more detailed analysis. So you will do that because you want to do what? You want to select your switches, and you want to select your inductance and capacitance values, ideal values, right? Then you will start considering losses. Then you will start considering dynamics, right? So it's several stages. So we're learning about the first stage, and we will also learn about the second stage by calculating the losses. We will talk about losses specifically later in the chapter. Okay, so we now have a minimum value of inductance. Is this what we will use in the converter? No, we want to make sure that we select a value greater than it. Again, we select inductance based on what? Ripple current spec. Right? You will be given a ripple current spec. So you can go to your waveform curves, and then, or you can go to the equation. We will do it both ways. But from the equation, this is the equation for delta I that you calculated initially, right? So delta I that we calculated here was equal to Vs dt over L. Fine. Just given a specific value of delta I, now you know what D is, right? Because we calculated the voltage transfer ratio. V output is equal to 1 over, so is Vs over 1 minus D, right? That was the voltage transfer ratio. So you can select, you already have D now. You already have D, you You already know Vs. You can calculate L for different values of switching frequency. You can do that. And we will see, of course, that L and switching frequency are inversely proportional. If you bring L here, bring L here, and delta I here, and then this is period. So bring this down to the denominator as switching frequency, and so you will find that switching frequency and the inductor side are inversely proportional. So you can calculate L now from here. I mean, you just make sure we calculated the minimum inductance just as a precaution. We don't want to be lower than this. But is it a step that you require to do? Not really. If you know what your ripple current needs to be, you can choose your L. But it's a good precaution, so you know that you need to be higher than that. So we went through this, we found L. L is inversely proportional to frequency, and we understand hopefully why, right? If frequency increases, what happens to your voltage across the inductor waveform? If this is my inductor voltage waveform, my inductance is always equal to delta lambda over delta I spec, right? Always. This is delta lambda. And this delta lambda is the area under the voltage curve. If I increase switching frequency, what happens? Yes, this delta lambda will become smaller because it means that this area will become smaller, right? If I increase switching frequency for the same duty ratios, then I have something like this, which means my delta lambda will become smaller, right? If my delta lambda becomes smaller and my delta I is the same, then I can live with a smaller value of inductance, right? If you want maintain the same ripple spec, if you're able to increase switching frequency, automatically your delta lambda will become smaller, and delta lambda is proportional to L, right? So larger frequency, smaller L for the same ripple. That's this equation. So from the curves you can do it without equations at all, really, without any equations. And we will draw all the waveforms like we did for the boost converter. So I think now is the time we need to draw all the waveforms because we need to figure out where this comes from. So now let's do our boost converter. Vs is here. I have my inductance, and I have my MOSFET here, my diode here, output capacitance, and load. Okay, we said that initially the switch is on. So if the switch is on, let me draw the voltage. Let me call this, because I call this the pole, I'll call this VP here. Let me draw VP. VP is the voltage across the switch, or basically the voltage between these two nodes. Right? What is that voltage equal to? When the switch is on, it's equal to 0. Right? When the switch is on, this voltage is a short circuit. I mean, the switch is a short circuit, so the voltage is 0. When the switch is off, it's an open circuit, then the diode is on. The voltage across the switch is equal to V output. Right? So this is the voltage I have here. How about the voltage across my inductor? Yeah. Yeah. The voltage across the inductor, when the switch is closed, I have Vs across the inductor. Right? When the switch is closed, I have Vs across the inductor. And how about when the switch is open? When the switch is open, I have diode is on. I have Vs minus V output across the inductor, and we said that V output is equal to Vs over 1 minus D. So the minimum value of V output is actually Vs. So V output so Vs minus V output is always going to be a negative number, 0 or a negative number, right? So let me draw something here. So this is Vs minus V output. And if this area is equal to this area, I know that everything is fine. I'm good, because I know that the average value of inductor voltage has to equal 0, right? So now I would like to draw the inductor current. So to draw the inductor current, we know that we start from the inductor voltage. Inductor current is the integral of inductor voltage. Integral of fixed value is a ramp. Starting from a minimum value, assuming continuous current operation, then this is inductor current, IL. Right? This is my inductor current, and this is its average value. Average value of inductor current is also equal to the average value of source current. Right? So if you're given, for example, this circuit has an output power of 5 watts, right? And it's an ideal circuit. And you typically know that, you typically know your voltage. Let's say you typically know your source is a 5-volt supply, right? If you know your source is a 5-volt supply, and I tell you this circuit, assume it's ideal and it's supplying 5 watts. What is the average value of 5 watts at 10 volts? Right? This is a boost converter. You typically know your load, right? Your load is typically, you know how much power it needs to consume, and you know what voltage it needs to operate at. So the output is 10 volts, and it's operating, and it's consuming 5 watts. What is the average value of inductor current? Come on. What's the average value of inductor current? What? No, average value of inductor voltage is 0. This cannot be, it has a value.
5/2.
Okay, guys. Power output is equal to
Yeah.
V output times I output, right? This is equal to 5 watts. And this is equal to 10 volts. So I can calculate
2.
I. From here, I is equal to half. Right? I is equal to 0.5 amp. I at the output is equal, average value of output current is equal to half, right? 1/2. So what is the power at the input? If this circuit is lossless, it's a 100% efficient circuit, then the power at the input is 5 watts. And it's equal to 5 volts times current. What is the current? 1 amp. Right? So this is average value of inductor current. Right? So now you calculated the average value of inductor current. What is the average value of switch current?
I'll just have duty cycle.
Multiplied by duty cycle. What is the average value of the diode current?
1.
1 minus duty cycle times the average value of inductor current. Now you have the average values of all the currents. And then you have the voltage rating of the switches, the switch and the diode. Now you can select your switch and diode fully with average value of current and peak value of voltage. Right? Next, we want to select our inductor. How do you select our inductor? You can go from the equation, or L is equal to delta lambda over delta I spec. You will be given a delta ripple spec of, I don't know, 10% of your average output current. Average output current is half an amp. So 10% of that is you can accept it as ripple. So it's what? 0.05 amps is your ripple current spec in that case. So you plug in 0.05 amp here. And then how do you calculate delta lambda?
Integral.
The area under this curve. You know your duty cycle, and you know your switching period. I mean, this is something you had to choose. I mean, it's you have to select a switching period or a switching frequency, or you are going to be given a switching frequency, and then you will iterate. Okay, this is not okay. I can go higher. If you go higher, you have to change your inductor value again. and iterate. But typically you will be given, you will select the switching frequency based on the switches that you select, the power loss that you calculate. This will be an iterative process. But assuming you're given your switching period and you know your duty cycle, because duty cycle is what you need for the voltage transfer ratio. This is independent of switching period. So you will select your duty cycle first. This is something you know. Then you can play with the switching frequency. Okay, let's set switching frequency at 50 kilohertz. Then I can draw this waveform. If I draw this waveform, I can calculate the inductance needed at a specific switching frequency for a specific ripple current. Right? Because I know where this is. I know that this is, the period here is capital D times T. T will depend on your switch. T is your switching period, or 1 over your switching frequency. Right? So this area you can calculate. This is without any equations. No equations at all, just the waveform. By understanding waveforms, you can calculate inductance. Next. So now I have inductance calculated, I have diode calculated, I have switch calculated. And inductance, I have peak current, I have Imax. Because I know my ripple current, what is you know, if you remember for inductance, we wanted to do what? We had to know the peak current and RMS current, right? So the peak current is this maximum current. And you have the value. So now we have peak current. And how do you calculate this peak current? This peak current is equal to, Imax is equal to the average value of inductor current plus delta I over 2. Delta I is a spec. The average value of inductor current you have from the power that you're trying to deliver. You're trying to deliver a certain amount of power. So you can calculate the average value of inductor current. So it's easy to do this, right? You can go in and estimate the parameters that I have for your various components in the circuit. So now we've selected L. Now I'd like to select or design C. How do I do that?
So then the waveform
You have to find first the waveform. I would like to calculate charge, right? So capacitance is equal to delta Q, which is the area under the current curve, divided by delta V spec. Delta V spec is, let's say, 5% of your average output voltage. Average output voltage is 10 volts. 5% of that is half a volt. So you're allowing a delta V of half a volt ripple. Right? So how do you now calculate delta Q? You have to draw the current waveform through the capacitor. So now, how do you do that? The current waveform through the capacitor is basically going to be affected by this current waveform, right? This current comes in here, and it's going to be divided up between the capacitor and the resistor, right? So what does this current waveform look like? The diode current waveform, what does it look like? We said that this diode current waveform is coming from where? It's inductor current after I've removed the switch current from it, right? So this is my inductor current. Part of it is my switch current, and part of it is my diode current. So let's draw the diode current part. The diode current only will be which part? The second part. So the diode current will be, so it's 0. This is my time when the switch is on. And then this is my diode current. Right? This is my I diode. Right? This is my diode current. Should I? Yes, ma'am.
Is that without the DC offset in the current?
I said this is diode. I didn't say the capacitor yet.
Oh no, I mean for the diode because it's going.
No. Let me erase and draw it bigger. Okay. Sorry. So let me. This blue. I'll start with the inductor current here. Inductor current looks like this. And then we said the diode current will be this is IL, inductor current, and this is I diode. I diode will be only this is my inductor current, and diode current will be this. And this is my circuit again for for your reference. Sorry. Right, this is the circuit again, and this is inductor current, and this is diode current. This is current flowing through here. This current, part of it will go into the capacitor, and part of it will go into the load, right? This is Kirchhoff current law into this node. It has to be divided, right? So, assuming this is a very large capacitor, assuming this is an infinitely large capacitor. If it's an infinitely large capacitor, what is the impedance to AC? Exactly. Once the impedance to AC will be 0. So anytime there will be an AC component, this will look like a short circuit. The short circuit is definitely easier for AC components to flow through here than it is to flow through the resistor. Right? So, and this current waveform is what? Is it a pure DC? No. If it's not a pure DC, then, and it has an average value. Because it's above. The area on top is greater than the area on the bottom. So it has an average value. So it's a waveform with an average value and lots of AC components. Right? So this is an AC plus DC waveform. For a very large capacitor, all the AC component will flow through the capacitor. And all the DC component will pass through. What is the DC component of this? Something around here. Right? It's the average value of this, almost. And if we assume that this ripple is not too high, then what is this average value equal to? No. Exactly. It's a diode average current. What is diode average current? What did we say? It's 1 minus D times the average value of inductor current. Right? Remember, inductor current is coming through here. It's chopped up between these two. That's it. It's, IL average is coming here. It's divided between switch average current and diode average current. This is my diode instantaneous current. What is its average value? It's diode average current, which is 1 minus D times IL. I assumed that this is flat, right? Because I said it's the peak value times the duty ratio that appears fine. I assumed it's flat, which is fine because we said that the ripple current is going to be 5% of your average current anyway, right? So it's very close. There was very small ripple in this case. That's why in discontinuous mode things are very different, because in discontinuous mode, ripple is, current comes down to 0 until a large value. So it's these assumptions I'm talking about you cannot utilize, right? But for continuous current case, with small ripple, it's okay. These back of the envelope type calculations are what you need to design your circuit, right? This is the average value of current. Okay, so now what did we say? The average value will now, since this is an ideal large capacitor, all the average value will go through and directly to my load. And all the AC component will go through the capacitor. Right? So I will take this average value, so I will take this instantaneous current that's flowing through my diode, remove its average value, because that's going to go straight to the load. And then everything else will flow into the capacitor. We agree? So basically I'll take this and bring it down, like we did before for the inductor voltage in the previous converter. Right? So it will look something like right, and this is I capacitor. And again, the area on average capacitor current is equal to 0, right? So always the area on top has to equal the area on the bottom. That is always the case, right? Because I removed the average value from this waveform. That's all I did here, right? So now how do I calculate capacitance? It's delta Q over the delta V spec. This is given, right? How about delta Q? Is the area under this curve. I can either take this delta Q or this delta Q. Remember, the two areas are the same. Which is easier to calculate the area for? This one, the square, the rectangle. This is when the switch is what? On. So this period is what? dt. Right? So this time period is dt. Right? So, and this value here is what? This is the capacitor current. Yeah, it's what? It's equal to the peak value. It's equal to what? Sorry, it's equal to what? Minus the average. I removed the average value, so it went down by the average value of current, of load current. What's the average value of load current? Average value of load current. Exactly, V naught over R. Right. So the average. So this here, the height, is the average value of current, which is V naught over R. Because I brought this diode current down by the average value of load current. Right. So the height is V naught over R, and the width is the duration, which is d times t. So this will be the delta Q. Okay? So let's see if I made any sense. Is everybody, are you okay with this? The waveforms? Yeah. So it will be small. This will be the ideal capacitance value, and then we have to include ESR, right? ESR, you have to include ESR, right? So you definitely, this is the ideal minimum value of capacitance for a specific voltage spec.
Will the calculated minimum capacitance, will it be correct enough for the assumption that you assume the capacitance is very big, that's why everything...
Initially, I assumed it's big. Why? To draw the waveforms, right? But now, I go back and give it a ripple spec, specify a ripple spec, and then calculate capacitance again, right? So you assume it's big to be able to calculate the inductance, and then you assume the inductance is big to be able to calculate the real value of capacitance. Does it make sense? Right? I assume the first one is big, then it's...
No, it's just you assume the capacitance is big enough that all the AC components go to the capacitor, right? So what if you then calculate using the dq over dv, delta charge, change in charge divided by the ripple spec. What if it gives you a capacitance that's like in a micro scale?
It is. This is not going to be infinite. So this I assumed. Yeah, I get your question. Yeah. So we assume this was the diode current waveform. I assume that 100% of the AC component is now going to flow through the capacitor. That's my assumption. So given this assumption, I calculated a certain area under this curve, and I calculated this capacitance. Sure, this capacitance, theoretically speaking, should allow all the AC component to go through, theoretically speaking. But in reality, I have a resistor in series with the inductor. I have a resistor in series with this capacitance. I have a capacitance value that is plus minus 20% of what I'm thinking it is, because that's what the data sheet tells you. Right? So in reality, you will never be able to allow 100% of the ripple to go through. Right? So I don't know if it makes sense, if I make sense or not.
You go back and recalculate.
Yeah, because I will calculate the area under the curve. This is the area under the curve. Then I will assume a spec. I can make this spec for a ripple infinitely small. Because, okay, there's a step after this actually. There's a waveform drawing after this that comes. So if you calculate, if this is your capacitor current, what does the capacitor voltage look like? Right? There's one more step that I didn't do. Right? IC is equal to, what is VC is equal to 1 over C integral of IC dt. Right? So, yeah, you have a negative current, so you're discharging the capacitor. So you're starting from some initial condition, you will discharge it. And then what? And then it's a ramp. Or you can assume, again, we said that the ripple is small, so we can assume this is small. If it's small enough to look like flat, what will the capacitor voltage look like? It will ramp up like this. If it's not small enough, which is this is the case, if it will look like a second order sort of curve, right? So like this, second order curve, like this, second order curve, right? This will be the capacitor voltage, and this will be my capacitor voltage ripple, my delta V that I've calculated for that specific value of capacitance that I've assumed, right? Because it's finite, it's a finite capacitance. I did not choose an infinite capacitance. I assumed it was infinite and looked at all the current flowing in it. All of this current, if I had put an infinite capacitor, would have produced 0 delta V, no ripple at all, right? But I assumed a certain voltage ripple, right? Because I assumed voltage ripple, then I came up with an actual value of capacitance. Then I can draw the voltage ripple, and then we will have to add to the voltage ripple the effect of the ESR, like we did in the last converter. So I will stop here. I think we did that last time, but I will review it quickly next time. But basically here, this is what we discussed, right? This is the delta Q is equal to the area under the curve, which is V output over R, average value of voltage over R, times dt. And then you can calculate delta V from, this is a delta V spec given, and then you can calculate capacitance from there. That's what we did, basically. So then the next thing they do is they add the effect of the voltage ripple due to the ESR. So what is the current flowing in the ESR, in the resistor? It's the same current that's flowing through the capacitor, because the ESR resistor is in series with the capacitor. It has a peak-to-peak value of delta I. This delta I is equal to the maximum diode current, which is equal to the maximum inductor current. So this is delta V due to the ESR capacitance. So now you have a delta V due to the ESR capacitance, and a delta V, theoretical delta V due to the ideal capacitance being there. You have to now make sure that your delta V spec is less than both of these added together. Then you go back and calculate your capacitance again. Right? You see the process? And that's the end of the ideal boost converter. So we will talk about the non-ideal boost converter next time. Yeah.